now ready for our second talk of the day. Of the workshop. Thanks. So our speaker is Kolaczyk from Boston University, who of course has written a wonderful, at least one wonderful book on that. I think you have two.
Two with one more coming.
It's like a N+1 situation here. So Eric is going to speak about dynamic causal networks and multi-scale temporal structure. So please take it away.
Okay, thank you, Sophia. Thank you for the invitation. I have some sense sometimes as to what it takes to organize these, so very much my hat off to you. I imagine also you're thinking last workshop, phew. So I'm going to talk to you about a project in dynamic networks that we've been working on for about a year and a half now with various stages of improvement. Let me get my thing here. A small caveat, I flew in yesterday morning. Jet lag is pretty good for the moment, so I think I'm all right, but if I start kind of going like this, someone give me a nudge and hit reset, and I'll keep going up here. All right, so what I'm going to do is start at 10,000 feet. I want to give you a little bit of sense of background and motivation, and then I'm going to start going through layers, easing into what it is that we're doing here. So it's about the last half of the talk where we start getting down to this is my model, this is my inference, blah, 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 blah. Most of the rest of it is going to try and give you some background. Turns out this project has been kind of fun for me. I've been doing networks for maybe close to 15 years, but the first 10 years of my career was actually in wavelets with multi-scale modeling, signal processing, image processing, stuff like that. It's the first time where those two worlds have met for me is in this project. So it's been kind of a fun project to bring multi-scale modeling together with network modeling. But because it's sort of uncommon to see those two together, that's why I'm going to spend a bit of time trying to lay some background for each of them. Okay, so at 10,000 feet, here's two very simple observations. We have all around us automated simultaneous monitoring of units in large complex systems. Right? You look at biology, you look at social media, you look at the internet, right? This has become kind of a paradigm now in our modern society. Very often we're doing this in time, and so one way of looking at the low-level data that we're looking at is high-dimensional multivariate time series, where these might be very high-dimensional that we're working with. Right, and so the implication here, and it leads to sort of a great deal of work already in dynamic networks, and I think workshops like this, is people put together the idea of saying, well, I have a system I'm interested in, and networks have become a very common way of representing the interconnectedness of systems, and I have time series, so a natural modeling paradigm to think about is dynamic network modeling. Right? And so that's the raison d'etre for what I'm looking at today. Right. So the particular application we have in mind is one from neuroscience. So I have a colleague, Lucia Vaina, in our biomedical engineering department. She works with various modes of imaging in the context of computational neuroscience. This particular mode that we're looking at here is MEG imaging. So this is a type of imaging that is typically said to have very poor spatial resolution but very good temporal resolution. And so they're looking at networks that if someone working in the field of complex networks would find embarrassingly small. They're 2, 3, 4, 5 nodes, but they're the ones that are important to them, right? On the other hand, the temporal resolution is really what they're gaining through this and why they're particularly interested in it. They're working with people doing, this is task-based MEG. So the task here, I tried this once myself. I had to sit down afterwards. It was a little odd. There's a vertigo that comes with it. You're watching a blank screen, and there are these dots here, right, that at some point appear, and then all of a sudden they start moving, right? And so those of you who've had that sort of effect, you can imagine it's a little disorienting. You're supposed to be able to push a button when you feel that you found them moving. Right? And there's something about that and the connection to certain parts of the brain and the timing of the dynamics as to when exactly people register that and all that, that's important to the problem. I don't claim to have the comp neural background to be able to tell you more than that, but that's the essence of what they're looking at. Right? So ultimately what we're going to be interested in is trying to infer networks that show you when certain parts of the brain seem to be talking to each other. So this is in the spirit of what are so-called functional connectivity networks in comp neural. And what they came to us was with something where, as I'll talk about later, there's already a number of methods in this space. They came to us using a method that used fixed moving windows, and they would just move them over time and infer networks within those windows of time in a certain sense that, again, I'll make more precise later. And they were talking about changes and how things could be very sharp changes, and the dynamics could be of one type when you're just watching and then all of a sudden change quickly. I said, that sounds like you have kind of a multi-scale phenomena going on, right? Drawing back on sort of, pulling the cobwebs off my older way of thinking and stuff like that. And so that's part of what motivated us to start thinking about multi-scale frameworks for modeling networks of this type. Okay? So what I'm going to talk to you about is a framework for dynamic network topology inference. I would say this fits in a very general sort of paradigm. People have systems level questions of interest, so they go about collecting multivariate time series data. If time series is a particular modality they can collect. They construct some sort of network-based representation of the system, and then they use network-centric answers to answer the systems level question. So they may say, I'm interested in things about groups and their sizes and which ones are linked. Ultimately, after putting together a network, they may do community detection. They may say instead some of the types of things Tom was talking about, where there's social theory, for example, driving things. Again, they put together a network, and they're interested in things like triadic closure or whatnot. So that's what I mean by this general paradigm. At 10,000 feet, this is something that's done over and over and over. The step here, right, is the one that I'll be interested in today, right? It's known as network topology inference in the statistics literature. Sometimes it's particularly called its association network, right? There's many types of ones you might infer, the particular type of one. And we're going to be talking about is modeling and inference of dynamic versions of these. Okay, so a little bit of background. In these contexts, there's already a huge literature on network inference, and I like it to look at it as a statistician as being characterized by choices, right? There's lots and lots of choices that distinguish the contributions. There are choices in what notion of association you mean, right? People like to talk about the network. Here's my network. Right? And I like to back them up a bit and say, so, what are you studying? So, what questions are you interested in? So, where did this network come from, right? And very often, it's, there's something like, well, and I use correlation, or and I use mutual information. That's considered a small detail, and then they move on to what they want to talk to you about. And that's the one I usually slow down a little, and I say, well, let's talk through correlation and mutual information, because each of them are a decision, meaning, saying, they're dictating then a certain meaning to the edges in your network, right? And so when I'll show you also a certain choice. There's methods of inference, right? There's testing-based methods, there's regression-based methods, etc. Once you come up with some notion of association, right? So correlation networks, for example, often in computational biology, will take gene expression from pairs of genes, compute a correlation in a Pearson-type sense, use some sort of standard t-test with appropriate multiple corrections to be used there, right? On the other hand, you have very fancy regression-based methods in the spirit of lasso-type algorithms and whatnot, right? So there's a whole range here. Choices, choices, choices. Each of these also have working parameters. There's some sort of smoothing parameter in the regression sense. There's a significance level in the testing sense, etc. Right? Very often, these methods are also trying to exploit and assume sparseness that people are assuming is going to be in the network. Okay? So we're going to have elements of all these types of things in the particular method that I'm showing you, but I want to show up front that there's choices to be made. We have a certain choice, and I'll show you what that is, and that's made in the backdrop of the larger set of choices that one might make. Right? I like showing this slide, so I'm just going to show it as an aside here. Choices really do matter. There's whole threads of discussion in individual domain areas. So Comp Bio has whole papers on it. Comp Neuro is very much struggling with this right now. Where it's like, well, do they really matter, right? And that's sort of initial question that's often, eventually we get, yes, it matters. And then question is, well, what's the right one? And woof, that's sort of a question for maybe the end of the day with drinks and stuff like that, because those discussions go on, right? So here's something just to show you that it does matter. what I have is gene expression data from collection of experiments on just 3 genes. All right, this is in E. coli, if I remember correctly. And what I've done is I've shown one gene plotted against another over the roughly 400 experiments, another gene plotted against the same one on the y-axis, right? And so if you look just at the blue here, the idea is that if I'm using correlation to decide if there's an edge between these two, this is the simplest version of what one might use, right? Then I would say, well, here's correlation of 0.43, here's one of 0.85, and if I compute a p-value using your standard Stat 101 machinery, I get incredibly small p-values. I say, yay, there's an edge, right? And now I know there's more context, there's more genes and whatnot, but for just this choice, that would be the decision. On the other hand, if I know a little bit about comp bio, and I know a little bit, I won't claim to know a lot, then I know that we have things like transcription factors, so we have genes that may be driving other genes, and so seeing that correlation may really just be the fact that there's some other gene that's driving those two in a latent sense, right? And so you could say, well, to adjust for that, I might use partial correlation, right? Where formally I would regress out the effects, say, of this gene LRP from each of TYRR and AROG, right? And then I would look at the correlation of those residuals, right? And so now I say, well, actually, the partial correlation, if that's my measure of what I mean by relatedness or association, that's only 0.27. There's a p-value of 0.92, right? So no edge, right? On the other hand, here I have 0.82. It really didn't change much to have adjusted for TYRR, right? And I have a very large p-value. Again, this is just a story. This is a large framework you would typically work with. There's a whole set of machinery and whatnot, so this is just for illustration. Finally, if I took all of the transcription factors in this particular data set, just to show you how things can change, right, I can make the slope become negative in this case, and I can significantly decrease the correlation here, right? So the point of this is not to cast all doubt and certainty, and say, well, gene networks out the window now, right? It's just to say that it really does matter what choices you're making. And at the end of the day, practitioners will make a certain choice, but hopefully in working with them, they should do it in a way that they understand the implications of the choice. Okay, the other choice to be made in this particular context is how to deal with time, right? So we're going to work with dynamic networks, and we know from, yeah, Andrew.
Application dependent problem, but in the application that you mentioned before, the neuroscience, are you sort of comfortable with the measurements themselves in terms of how you spoke about the resolution being low, but in terms of noise and the particular technology, how they're getting the actual numbers? Sometimes things start off as images, sometimes they start off as counts, and they end up being...
in terms of all the pre-processing that's being done.
I'm just saying in this particular, I know because every application has a long story, but just is this one where you're sort of, you as a statistician...
I'm comfortable as a statistician with the knowledge and quality of the work of the group I'm working with being as state-of-the-art as that state is currently in art. How is that, right? There's a years ago at the...
Said, by the way.
Thank you.
Going into politics.
Oh, go into politics? No. I don't even want to talk about politics. Thank you. We're still hurting a little, some of us over in the US. I will say, though, at the joint...
want to visit right now?
No. I will say at the joint statistical meetings in the U.S., they sold T-shirts, so they still T-shirts. But the years ago, they used to sell one, for some reason, for little kids. I have no idea why, but I have still an image of a toddler wearing this. And it says, statistics is never having to say you're certain. And so I always like to bring that one out when I give an answer like that. All right, so the choice of what to do with time, right? So if you think about what you know about time series analysis, or more generally non-parametric function type analysis for sort of time index functions, there's whole classes of methodologies. There's kernel type smoothing, multi-scale type methods. There are formal time domain methods, spectral methods, all of them making some kind of assumption about what sort of structure we think is going on in time. And so I'm going to bring in a certain perspective here, motivated by the story I told you earlier about changes at multiple time scales, and say, therefore, what I'm going to do is bring in a multi-scale analysis. Certainly for this data, there are all kinds of other things one might do, As far as I know, there is no pairing of multi-scale analysis and dynamic networks to date, and so this appears to be the first trying to put those two together. It seems like we'll look at the end to see what sort of usefulness that pairing happens to do. All right, so our focus here is going to be on making a particular choice of network model. We're going to use vector autoregressive models or so-called Granger causal models. When I say causal, I always have quotes around the causal. I see it as a vector autoregressive model, but in the neural group that I'm working with, they come from a part of the literature where Granger causal was the terminology being used and propagated through. So I'll use them both interchangeably here. And then for the multi-scale modeling, wavelet type methods are sort of the canonical, traditional tool for doing multi-scale modeling. But what I'm going to do is a few slides to show you a bit later that we're going to actually adopt so-called partition-based multi-scale modeling. And this is something that in that literature, when it was very active, there was a certain trend in which necessarily it was easier to work with partition-based perspectives than it was to try and work with full orthonormal systems of functions. And I think you have something similar here, so I'll show you sort of why that comes in. All right, so let me give you a little background on the Granger causal models, a little background on the multi-scale models, and then I'll show you how we put them together. All right. All right. So xt is going to be my variable interest here. It's going to be an n-dimensional vector time series indexed by time t. The entries of this are going to correspond to what we have in mind as being units in our network, right? So ultimately, these things will be what I'm calling vertices, right? So these could be countries where we're looking at their financial records. It could be regions of the brain where we're going to ultimately look at the functional connectivity between them, and we're measuring time series for those. All right. We're going to adopt a type of vector autoregressive model with p lags here. Notation is that I'm modeling the behavior of this time series at time t as a function of its p lags, and I have matrices theta L here that are capturing the dependency between the two. Right? So what you can picture here is this is corresponding to all the nodes of the network as I go down the rows, right? And I have the same thing here. So these matrices are number of nodes by number of nodes. And then I have one per lag. So what you can picture is having a stack of matrices. That's your parameter space, right? This is for a time index model where the parameters, however, are not moving. We're ultimately going to define a non-stationary version of this. So we're actually going to let these matrix stacks change in time. Okay, so it's going to be a bit of an indexing nightmare. There's going to be multiple things going on here with that. Right? People typically say that xv Granger causes xu, right, if this particular coefficient is non-zero for some lag. Okay. All right, so in terms of making a network graph here, what is our particular choice of graph? It's going to be defined in the sense of a graphical model, right, which is similar to, say, concentration graphs in Gaussian graphical models, for example. Right? So we're going to take this collection of p matrices, and there's actually choices to be made even here. So I'm going to show you two choices that are common. I'm going to make the simpler one. Okay? So either you could say that G is a directed graph with an edge from V to U if and only if the norm of the vector that you get from this stack of matrices, right, by going to U and V and then pulling out the entire set of lags, right, if that has non-zero norm. So somewhere there was a non-trivial connection, a non-trivial dependency between them, right? That's one way.
And you're using just the matrix. I mean, what? Just the matrix.
Yeah, just the matrix, yeah. This is assuming I know this. At the moment, I don't know the value, and so that's the inference problem, yeah. On the other hand, you could use the elements of that vector if you want in a more complicated sense to define a multigraph, where you could talk about the connections between vertices based on a function of lags, right? We're not going to do that. That gets even more complicated still, and this was complicated enough. Right, so we'll focus on the first of these options. All right, so let me talk now about time index graphical models. Right, what we're going to do is we're going to cast a particular non-stationary framework. It's going to be a very simple one. Right, it's going to be blocks of stationary pieces. Right. One can be more careful and build those blocks in such a way that they're sort of well-defined in a sense of a formal probability space across the entire time interval. We're not going to go through those details, but one can do that if one wishes. We're adopting a change point perspective, so really what we have is piecewise Granger causal models, right? This is going to give us then, if we index those models by now the thetas changing in time, then it's going to give us at any given time instant a time index graph. And that will be the definition of the particular time index networks that we have. And so our goal here is going to be to infer the chain points that are distinguishing these stationary intervals, and within each of those intervals, infer the corresponding edge sets. All right? And I'll give you details on all these. All right. There is already a great deal of work. It's a very active area, both generally and within statistics, particular for dynamic network modeling. I make that comment purposely, right? Things being very active in networks and things being active on the same front in statistics have traditionally not been the same thing. We have caught up very much as a field in many ways, I think is very good, and we're much closer now to sort of the forefront of what's found interesting in network science in general than we were, say, 10 years ago. And this is one of them where I think we're right there with the stuff coming off the presses. I believe, George, you're going to talk. George's going to talk much more about this later this week, so that does me a favor of needing only to have a handful of things up here, and I have one of George's papers up there, so I'm safe. There's seminal work in the flavor of the type of inference algorithm I'll show you by Meinshausen and Bullman for static graphs. And then there's a sub-literature that takes that type of methodology and has moved it now into dynamically changing graphs, most of it where it has stationary time series, and some of it where it's beginning to allow non-stationary time series, right? Our work is going to take these ideas specifically in the multi-scale direction, as I told you. So, last bit of context, let me give you a little sense about the particular flavor of multi-scale modeling that we're going to use here. So starting, say, in the late 80s, right, and really going back on threads, going back at least to Haar with his well-known paper in 1910, there was an explosion of development of methods of multi-scale modeling, right? These were a big deal at the time in the sense that they were mathematically principled, they were computationally efficient, going back to some of the work of Malat and his fast algorithm and whatnot, and they were very applicable for certain domains and problems. Right? In particular, they filled a huge gap in signal and image processing that had been, in some sense, either not wholly recognized at that point, and even if it was recognized, we didn't have technology anyways, for doing things that Fourier-type methods couldn't. Right? So at that time, at least, it opened up an entire new forefront in that area. The quintessential example of what did that was orthonormal bases, or more general bases, of wavelets. Right? Interestingly, after maybe the first 5 or so years of development, as people started pushing the forefront of this onto other areas that weren't simply a time series or an image, we found that it got hard quickly, right? Which I guess is a good thing in a way. But you want to have it be hard quickly, but with traction. And things that were particularly making it hard were non-normal noise, right? Because wavelets being orthonormal bases, working with normal noise, could transform problems into normal noise problems, and basically everything was still very nice. You knew a Poisson type noise or other things like that, working with orthonormal bases became non-trivial. Or working with structured data, working on things that were, say, on manifolds, on graphs or whatnot, that also made it where the mathematical bottleneck was fairly substantial in being able to change the underlying multi-scale representation in a way that kept all the properties. There was a couple people who pushed a different agenda. One of them was a seminal paper of Dave Donahoe in '97, where the paper is, the title sort of belies the impact that it can have. It says CART and best ortho basis, so CART being regression trees, right, and best orthonormal bases. The paper basically set up the idea that all the key elements of doing a traditional orthonormal wavelet basis were essentially representable in a binary tree representation of partitions, where the partitions had a hereditary structure, that if you want to split an interval, say here, you have to split it in half first, and then you split in half, and then you split in half, or whatever, right? So it was a particular type of partitioning that linked to certain trees that ultimately could be shown in various problems to have properties very similar to wavelets. And so that led to a slew of papers that started exploiting that idea in these contexts where going with wavelets was not as easy. And I would say that when we sat down with the idea of trying to do this particular project, my initial inclination was, I'm not going to try and put wavelets into this because I can do it much more quickly and much easier using partitions. Right? And so that's what I'm going to show you here. To give you an example of what that's doing, generalized linear models was one place where it was tricky at a given point in time to figure out how to actually put in multi-scale modeling. We have some work where we worked with generalized linear models and we did so-called piecewise polynomial models on particularly multi-scale pieces. Right? And so here's an example of what I meant by a generalized linear model. This would be time indexed as well, but now P of xt has a exponential family form. Typically you would say the function through which you're getting these discrete theta t's over time is a member of some sort of inhomogeneous function class, like a Bessel ball or something like that. That would be sort of at that point in time the bell that would suggest, multi-scale wavelets, right? It also is something that could suggest piecewise polynomials on the type of partitions that I'm talking about. Turns out from an approximation theory point of view, they have exactly the same properties, and therefore you can use one or the other from the point of view of the risk theory. From the point of view of doing the model fitting here, what we did is complexly penalize piecewise polynomial estimates, where you're doing penalization of the log likelihood. We did just a counting penalty, where you're asking how many elements are there in the partition, right? So the partition you're working with is something like this is time going from 0 to t, and I might have something like that, which I can achieve by a split in the middle, a split in the middle, and a split in the middle, right? And that's why it has a certain nested sense to it, right? So this, wrong button. So this PD star here is talking about a complete recursive dyadic partition that corresponds to a balanced tree, a balanced binary tree, right? And then this is saying I'm looking at optimization over all subpartitions of that, where for each of these particular subpartitions, I fit polynomial pieces on each of the individual intervals, right? And I try and optimize over all of those. Right? So with an appropriate choice of penalty that has a certain additivity property in the tree here, you can do this in essentially an order big O of t algorithm, where what you're doing is making on the order of number of time steps model comparisons, where you say, do I say this is one homogeneous interval, or do I make a split? Right? And I say, is this a homogeneous interval, or do I make a split? That type of decision-making process is replicated the whole thing. All you need to do is basically know the complexity of that process, and then you simply repeat that. Right? The typical way these are implemented is like decision tree type algorithms, so it has an up-down algorithm to it, and that's where you can get your orders of operation here. You can also extend this to go beyond recursive if you want, in the sense that it's
a penalty for changing things too much, because otherwise I would want to divide into infinitely many partitions.
Yeah. So first of all, there are two constraints. One constraint is that you have only up to the resolution of your data, right? So if I have t time points, then that's what I have. As you would get more data, you have more to work with to make these decisions. The other one is the penalty here, which is the number of partition elements that will be penalizing you directly for what you're saying.
I see, but you have nothing like sort of that you would constrain the derivative of something like that. You don't want things changing.
So I'm not doing, for example, a spline-based fit. So what you'll see is with these piecewise methods, what you do get is the one disadvantage of piecewise, which is you have discontinuities here. Yeah. So you could, in principle, we can talk after. There's ways one could adapt this and smooth it if one wants. So yeah. Okay. So this is the spirit of what I'm going to do with the networks. I'm going to take what I showed you with the Granger causal models, right? And we're basically going to set up a similar type of thing where I'm now fitting networks within each of these time periods. Okay, so it's a multi-scale Granger-based dynamic network modeling framework with corresponding inference. We're going to partition the time space into blocks. Each have independent stationary var models indexed by block. We penalize blocks still using a counting penalty. We do neighborhood selection with each block using a group lasso. The group lasso is going to be because you have this entire vector of dependencies across lags that are going to be determining whether or not I have an edge. Yeah, Andrew.
Eric, maybe you're going to say this. So in finding the partition that you're in, do you essentially grow and prune, if I can use the cart terminology, or are you just growing?
It's a growing and pruning. Yeah, this up-down algorithm that I was talking about, that takes care of both of those. Yeah, it is literally, you're literally solving that optimization. It is if you use a penalty that has a certain additivity structure in that tree. Yeah. Is there another question? No? Okay. Okay, so let me show you with a toy what we're doing here. We are first of all going to take a neighborhood by neighborhood approach. This is going off the original Meinhausen-Bullman neighborhood selection type approach. So we're going to do the same thing here. Without loss of generality, let's say we're always talking about a node U, right? And then you would get your network by taking the union of all these different neighborhoods, right? So for node U here, I have 3 different network topologies. And I'm saying that starting at time 0, this one maintains until time 6, where I get my first change point, right? At time 8, I get another change, right? Where from time 6, I go from here, having 1, 2, 3, 4 edges, all pointing into U, to here, where I only have 1 edge pointing into U, right? At time 8, that changes again, and I get a new edge going from D to U. All right, what I'd like to do, if that's my truth, and I'd like to infer where these taus are, and I'd like to infer these structures in each of them. All right. The recursive dyadic partition is going to be the one I show you. We also have implemented the recursive partitioning where you don't have to stick to dyadic splits. Nominally, that's much more expensive. It's an order time cubed algorithm rather than being linear in time. There are tricks for that as well, though we haven't implemented them yet. All right, so the idea then is you're making a decision for this interval versus a split into these 2 intervals. For each of these 2, you're making a decision of this interval versus a split into each of these 2, right? So your calculations are a whole bunch of these comparisons of parent versus children, right? And then the up-down is a way of processing those decisions so you have a consistency of the hereditary splits that I was talking about. All right. So here's the analog of what I showed you a few minutes ago for the generalized linear models. This is what we've set up now for the time series problem, right? So because we're dealing only with the neighborhood of U, right, we can condition on the rest of the time series. We have a conditionally independent model here, which says the parameters that I need to go after now are these thetas, right, over lags L across time t for every pair of vertices UV. Right, but because we're being centric to U, this is all vertices V that we're talking about, right? So this is what we're inferring. We adopt a complexity penalized estimate, similar to what we did before. So you have minus log likelihood plus twice a certain penalty here. This penalty is a sum over vertices of simpler penalties. I'll show you those in a moment. XU is your time series specifically at node U. Script X is the data for all the others. This gamma t here is a space that is allowing us to work with similar ideas to the stuff I showed you earlier for the generalized linear models, right? What this does is it says this is a space where I have time-varying vectors. This is the dependency across lags. And I'm going to let them vary in such a way that for the risk theory we'll do at least, those are going to be piecewise constant in norm. And that's going to be a way to allow us to access some of the technical machinery that have been used in previous types of projects in time series and image processing to use here, right? And then this penalty here is going to have 2 pieces. It's going to have something that's penalizing the number of change points that we make. So this is very much like we had last time. And it's going to now have another penalty, which is within each interval defined by the partition corresponding to a candidate estimate theta tilde, right? We're going to look at a penalty penalizing the norm of that vector of dependencies, right? And so this is a group lasso penalty, and this is a counting penalty, right? This is penalizing networks not getting too complex if they don't need to be. This is penalizing not making too much splits in time if you don't need to, okay? All right, and there's some details here regarding the partitioning. The partitioning is actually a union over all of the possible vertices that may connect of any of the partitions that they call for. So that it's a in Tom's language, it would be an actor-oriented perspective here in defining the partition. If any of my neighbors need to have a change, right, then from my perspective of the changes dictating my time series, there'll be a change point. Yeah, Carrie?
Am I surprised at the 2 norm, Eric?
Surprised at the 2 norm error? I don't know. Are you surprised?
That's what I'm asking you. Is that
No, I mean, if what we're doing is pulling down group lasso type tools, and this would be a standard choice. There's many flavors here as well one could use.
but wouldn't you rather do something else if you had the machinery, or not? So if you weren't constrained by machinery for which norm you wanted, would you still pick the 2 norm? Maybe
I would say for what we're doing here, we're comfortable with it. Could you do other things? Yeah, there's a whole subliterature just on how to replace elements of group lasso, and we're trying to keep those. We're trying not to put the novelty there. Yeah.
Okay, you got other problems.
Yeah,
Okay.
yeah, exactly. Yeah, I got lots of problems, Gary, including the guy in back there. Yeah, please.
Eric, I missed something. Where are the lags, the memory within the...
So I have now subsumed that, and so it's a good question. I am not penalizing the lags here. You could build in another piece where you would have that. The lags are...
Different time intervals, you can have different...
You could have different, from the computational perspective, you could here. We haven't done that. From the theoretical perspective, we definitely haven't done that. We use a fixed number of lags across time in any of the intervals. And that's subsumed in the sense that these are p-length vectors where p was the number of lags. Yeah. Okay. All right. So let me show you, running close to the end here. So having done all that work, now let me just show you in a handful of slides the theoretical results we have to say about how you're doing here and some initial computational results. All right, so basically 5 slides. Yeah, Andrew.
Last question.
Yeah, go ahead.
The tree structure of the partition give you interpretability in the way it might? I realize this is far more complicated than standard card analysis, but that was one selling point of card initially was that...
I would say card is actually more complicated in the sense that here you only have one variable you're splitting on. Cart typically is many variables. This is complicated that within each interval we're doing something fairly complicated by associating a network. So to give you interpretability, I would say what it gives you is change points. And really you should just think about it as a change point analysis where I happen to define change points in the context of the partitions to be able to put together the rest of this machinery. Yeah. Okay, so what we're going to do is look at 3 things, right? We're going to look at what happens if I want to just look at this subproblem that I said keeps propagating, right? Is do I split an interval or not, right? If I can't do a good job on that, then sticking in a large framework is not going to work out well, right? So I want to say that I can do a good job with that. On the other hand, if I have one interval now defined, and I say it's stationary within there, and I want to infer the network, I'd like to be able to show that I can do a good job with that for the same reason. And I'm going to do that a whole bunch of times. And then I will show you a risk bound that gives you a sense within the overall model class as to how from a certain measure of risk you're doing. And it's the usual thing, you look at the right-hand side bound and it shows you how the different parameters of the model are indicating the accuracy involved. Okay? All right. So here's a very simple sort of statement. The proof are in the spirit of some of the stuff that George and colleagues have done or Rob Nowak and his folks have done. Suppose I'm just looking for a single change point at time t over 2 right in the middle, right? So it's perfectly set up for dyadic type partitioning, right? And I'm testing either that there's no change point, meaning that my partition is just the interval 0t, or that there's one change point at that particular spot, right? And I'm using just the group lasso penalized least squares. You don't actually need the counting penalty because this is just one of the subproblems, right? Then under appropriate assumptions, you can show a certain type of consistency, saying that under H0, the probability you decide correctly goes to 1. Under H1, the probability you decide correctly goes to 0, and this is asymptotics in the number of time points. Okay. All right, so that's a good sanity check. Result number 2, right? Setting that weight parameter on the group lasso for just how we infer the networks. That's an important thing, right? One way that you can set that is by using a notion of type 1 error for the neighborhood. Right? And so there's work in the original Meithausen-Buhlmann paper 10 years ago now that had a certain type of definition that is in the IID context that you can also extend to the time series context here. And this says, given a particular choice of this parameter lambda here, the probability that the connected component of your graph to which your vertex u belongs. So it goes a little bit beyond neighborhood, right? It's saying your vertex u, the neighborhood you're looking for, and the connected component around it, right? The probability that the set that you pull down as a connected component around u based on your inference, probability that does not contain the truth is bounded by alpha, where alpha is a parameter that you can choose, okay? And these parameters here involve an adjustment for noise, and then essentially is using a chi-square argument that gives you.
What do you mean that X of U is homogeneous? I mean, homogeneous in which sense?
So this just means what I'm dealing with is no change point now.
Ah, okay.
Yeah, exactly. Right. So these are each two small subproblems. One showing how you do simply with choosing a change point. One showing how you do simply with choosing a neighborhood. Both of them, given the right tuning, given enough data in this temporal context, do a good job, right? And so then finally what we have is a risk bound. There's two pieces. One is setting up a general expression for which you can do various things for this particular problem. You say, given theta hat coming from the optimization that I showed you, now for the full model, right, with trying to find how many change points, trying to find what the network is within each of those. If you put a condition on the penalty that essentially says it acts like a well-behaved prior. This is so-called Kraft inequality from information theory. It's in more of an engineering information theory approach to doing this type of argument than it is, say, a concentration approach, but it's a similar type of idea. Then if you define a Hellinger type risk, then you have the risk bounded by a deterministic problem that you can then hammer away at. Right? So if you hammer away at that, you choose L2 error to define your risk. So you can use this and this to bound that L2 error. And given the model classes that we assumed, if we put an additional assumption that within each coefficient of dependency, it is varying in a bounded variation fashion, right? Then what you get for an L2 type risk, using a bounded variation assumption on each of these coefficient time series, is you get a bound on the risk that looks like this. And what that's saying then is that you get behavior that is driven by the number of samples in your problem, right? Roughly on a log t over t type scale. You have p entering there, and then you also have this lambda max. That's the largest eigenvalue of this x transpose x over t. So depending on the behavior of that will also be affecting it. Okay? All right, so I have just 2 more minutes left here, so let me just show you a quick illustration. One is a modest simulation study. My student is running more of these. You know, you can run them and show it does well, etc. Usually what I'm looking for more is sort of where is it breaking, right? And so that's what I asked him actually to show. And then I'll show you preliminary analysis of the MEG data that I used to motivate this. So the setup for the simulation design is very simple. Because the network that I was going to show you with the MEG also has only 3 nodes, what I'm showing you here is just a simulation from only 3 nodes. Again, it's an embarrassingly small network for a complex network audience, but it does interest directly our colleagues that we're working with, right? So this just sets up a lag2 type model. We're looking at the neighborhood of node 1 as a function of the influence of nodes 2 and 3. And we're looking at having a growing number of time points. And he actually looked at a variety of different nodes up to route 20. For that particular MEG they're working with, they wouldn't go much more than 20. And what you can see here is there's a triangle structure to this matrix where this is looking at increasing network size and increasing time series size. And as you're getting a longer and longer time series, the probability or the frequency with which you identify the one change point that he put in the model is going to 100%, right? But that's breaking down with increasing network size. And basically, as you increase the network size, you're going to need to increase the number of time points as well. Okay? So this is for recursive. You can also do this with just recursive partitioning rather than recursive dyadic. Until we implement some tricks to get over the cubic time for that one, that's really the bottleneck in most of what we're doing, is it just takes a while to run those. It's not network size for the moment for this context that's really dominating things. All right, so 2 pictures to show you here. This is your task-based MEG data. They know that they have a static period up to a certain point, a motion display up to a certain point, and then they're looking for a response. They have 3 regions of the brain that they're interested in, right? And what we're looking to do is build a network using the data on 6 subjects who each did this 160 times. That boggled my mind. I mean, I got vertigo looking at it one time. I cannot imagine doing it 160 times in one sitting. So I'm thinking they're probably undergraduates and they're being paid, right? So this is what you get as an initial visual representation of things going on. So the blues down here, if any time over 160 time points, trials, there was that time point being declared as a change point, then we put a block, a little line of size 1. So you get that called 3 times in 160, you get a block of size 3. Okay. There were roughly on average about 10 change points per any particular trial, per any subject. So this looks very dense, but really any single one has roughly about 10 time periods. The gray lines here, this is when you start, this is when there's nothing going on, the baseline. This is when they're watching. This is when they're supposed to, here or afterwards, supposed to have made a reaction, right? And what our colleagues are hoping for is to see some kind of changes that are visible. These are the norms of the lag vectors for each of the 2 network nodes, the FEF and the V3A network nodes, right? And so you can see there's definitely some things going on here. I'm being told they're thinking about this, which I think means that they, like us, see that it doesn't look like there's some kind of very crystal clear hit the button and boom, there's some massive change in the network. I don't think they're expecting massive, but I think they're expecting better. But that's science, that's collaboration, so we'll see where the discussions go. Okay. All right, let me wrap up here. Dynamic network analysis, I think, is certainly one of the frontiers right now in network analysis as a whole. And as I said, it's very nice to see the statisticians as well, or maybe uncharacteristically have jumped in early on this. This is good. Neuroscience, and I didn't talk much, but economics and finance also has a great deal going on here. I've been at some workshops where there's all economics people, and I show this, and there's sort of, you can see in real time the calibration being made to realize there's a whole subliterature that they can be looking at there. The synergy across these types of fields is interesting. It's also inherently an ongoing danger, I think, for network science as an overall field, to have these parallel threads in areas that may not speak as much to each other. And statistics, applied mathematics, and computer science and such are often the glue between them that can really help these communications make sure that they're made. All right. Here in this context, I think we're fairly pleased with most of the decisions we've made and the results that have come out on the development and the theory side. What I'd like us to do more is work on the empirical study with the MEG data. There is no paper right now, but there's a draft that should be out in a month or 2. So, thank you.
I was surprised by a very early choice you made, which was actually the fact that you assumed that the autoregressive component was 0. Is that right?
The autoregressive is known, but not 0.
So you said something
was
like
what
theta UU was 0.
Oh, I'm sorry, the autoregressive, yes, yeah. That was convenience, again, for the theoretical work. We can talk offline about it. We can definitely make changes on that. Yeah. Realistically, yeah, I agree. Yeah.
I have a question regarding the recursive dyadic partitioning. Like in the change point detection literature, people use an algorithm, binary segmentation, which actually maximizes a criterion and partition the interval and do it until there is no more. So do you think this dyadic partitioning and the
basically, yeah, there's depending on the literature and whether you CS engineering, statistics, they're all variations on essentially the theme as I understand it. Yeah.
Okay.
Yeah, please.
Is your EEG data possible, like time series has co-integration or integration such kind of non-stationarity? I don't think it could be done by that.
Could one use co-integration? Is that what you're asking? Certainly. I don't know the particular literature on MEG to know what has or hasn't been applied, but I wouldn't be surprised if it has not already.
I think your methodology kind of cannot solve this if you don't take certain difference. It's hard to deal with like this kind of non-stationarity if you do partition, only do partition.
I'm not sure I entirely understand the question. There is pre-processing that's done, for example, and so you can. I haven't talked about the pre-processing. There's a large amount of pre-processing you do, which I think is part of what Andrew or Carrie was asking me earlier, where I gave my political answer. Yeah. George.
So under the hood, you have an assumption on normality.
We do have an assumption on normality there, yeah, we definitely do. Again, it's one of the natural directions to
How close are
extend.
How do you need to do pre-processing?
You have to do some pre-processing, certainly. Most of what I understand they currently do involves normality type assumptions, and so they are incorporating some of that. I have to say, though, my sense is that, I don't know, I mean, you might know better than I do, whether someone has brought in the non-normal type models into the dynamic regime. Certainly in the static regime, some of that stuff only in the last few years, like in the comp bio literature, has really started bringing in fairly carefully the copula-based methods or some of those things. I'm not sure in dynamic if everyone's done it
For
yet.
voxel and for very, very small models, there is an archive paper by Gervais Rasputin.
Okay.
With Poisson. And he goes
With Poisson, yes, yeah.
for the voxel.
Okay, right. No, that one I have seen. I was thinking more generally, sort of the type. Yeah. So I think in the static literature, people have only just sort of started cracking in a fairly solid way. Gaussian graphical models that extend the Gaussian graphical model in the space and scale and whatnot that they do without putting the Gaussian assumptions on. Yeah. Please.
In the MEG data, I was wondering how you model the spatial structure that you know about. Do you use continuous data over the brain,
So
or do
we
you use
haven't-
some areas that you condense, or do you go to the dipoles, which are
So
supposed
they define regions of interest are their terminology for this literature, and there's a whole art and science, as I understand it, behind defining these. They're using
inside, which they invert from the
yes,
measurements,
they
or
are
do
they are
stay
they are
outside?
using regions that I believe these are 3D defined regions, and there's an integration. Then this is all part of the pre-processing would be an integration of the measurements from the much more voxel specific measurements. They aggregate up to these regions of interest.
But then when you analyze, you use small voxels, or you use a few regions?
No, we're using these large regions. So where there were these pictures, right? These are fairly large regions. IPS was one of them. It's actually the aggregate of these two here. V3A was another one there. Those were I would have to look at the details to remind myself as to how many voxels are going into those, but there's a non-trivial number that are going in there. And this is a good offline discussion in the sense that also in the comp neuro literature, as I understand it, that there's all kinds of discussion. Whether the surface, many things you might measure on the surface, but they actually don't tend to want to use this as a surface to talk about things like distance or whatnot, because connectivity is going in and out often. So I'm happy to chat about that to the extent I know it, but it's a non-trivial subliterature, just figuring out how to work it. Again, hence my political answer to the question that was asked. There is a ton of work that goes into all of that, and you do have to feel comfortable working with the people that you're working with, that they indeed make their living doing this, and they're doing it to the best that field knows how to do it right now. Yeah.
It's a discrete time model, so what about the definition of the time ticks? So because it's t minus 1, t minus 2, is there anything natural about the definition of those time lags?
The data that I'm working with here, if I can anticipate where I'm guessing you're going, the data I'm working with here has very fine time resolution. So the type of context you're working with, where they may be like 3 months or a year between measurements of a classroom, and lots can be going on here. As long as someone is comfortable that it's, say, millisecond or second resolution, there isn't sort of massive changes going on that you would want to be modeling. This is more in the time series literature spirit and less in longitudinal data analysis spirit.
But then
so we don't
if you
tend
say
to
that
worry
it's like
about
milliseconds, does that reflect that on the brain scale, what happens in our brain is something that where a millisecond is indeed something on which processes take place? And
there's some of that, but my understanding is it's more tied to the phenomena that's being measured. So the fact that the fact that you have just these lines here are indicating the scale on which, so this is task-based imaging, and this is the scale on which, in terms of tasks, they feel significant changes are being made. Now, I think the results are suggesting that there's more going on, even at the resolution we have here, much less at the resolution that they're dealing with here. I don't think they're really expecting for this data that at an even finer resolution than the time points that we're using here, that there's something that they're interested in going on. Yeah.
Have no more questions. Let's thank Eric again.